So we have a really fun show for you tonight. I hope you enjoy it. And let's dive right in to our beginning here. We've got Dr. Matt Golombek with us. And indeed, he's going to tell us all about that helicopter that's flying around on Mars. But first of all, we had him on our show. Gosh, I think it was back in 2017, if I'm remembering right. And we asked our audience where Perseverance should be sent. So let's take a look at what our All Space Considered audience voted on.
How many for Jezero Crater? How many for Northeast Syrtis? And how many for Columbia Hills? Ooh.
We like hot springs.
We like hot springs. So does that reflect the votes, what you just saw in the distribution here? Does that sort of reflect what happened?
No, it does not.
So tonight, Matt, our audience did not quite vote for where Perseverance was sent. Jezero Crater was picked, and fantastic location so far. But I'm going to let you tell us all about that. And thank you for coming back and joining us here at All Space Considered. I can't wait to hear all about what's been going on with the helicopter in Jezero Crater. Thank you again for joining us.
My pleasure. It's really fun to be back with you all, and what a spectacular location you have, and a treasure for Los Angeles. So I always enjoy joining you. So what is flying at Mars, and why do we care? So Mars is in a period of what I would call renaissance. There have been about 10 missions successfully flown to the red planet in the last 25 years. But why? What's so special about Mars? Well, first of all, it's the most Earth-like of all the terrestrial planets. It's the first other planet that humans will go. No place else they really could. It has seasons and days. It has an atmosphere and polar caps, and it has volatile exchange. So it's kind of like the Earth in a lot of important ways. But in others, it's really very different. It has a very thin carbon dioxide atmosphere, and it's so cold and so dry that liquid water would not be stable on the surface today. So you would actually be below the water triple point, so that you would either have ice or you would have gas, but you would not have liquid. And yet, when we look into the past on Mars, and one of my favorite images from the Viking mission 45 years ago, we see a very different story. We see these little channels. There we go. So there's a channel, and there's a channel, and there's a channel, and you can see all these channels that are going down to about the same elevation, which I'm kind of tracing out here. So they all flow down, they carve through the terrain, and they all end at what looks like a common elevation. So you could take a location here that is basically showing what the surface would have been like that had liquid water sitting on the surface. And I know that because all of these channels end at the boundary I'm drawing here. And there you can see some channels there. We go around here. And when I get to the lowest point here, I see a single stream that exits and flows out. So there's a natural dam here, and the water sat here for some period of time, and a long time ago. Now, how do I know how old this surface is? You can see there's lots of these big craters, and you can see these craters have flat floors, so they've all been filled in, and the rims are all weathered down and eroded. So something was eroding the surface, and if you were to count all of these craters, you would get an age of about 3.6 to 3.8 billion years ago. So what's so important about that? Well, it turns out that on Earth, life started at about 3.6 billion years ago. And the one absolute requirement for all life on Earth, everywhere, no matter where you go, is liquid water. And so the presumption is that if you found liquid water elsewhere, you would have a potential habitat for life there. So here's Mars right next door in our solar system, and it had liquid water at the same time that life got started on Earth. So I would say you could address one of the most important science questions we scientists can address, and that is, are we alone in the universe? Will life form anywhere that liquid water is stable? Or do you need some happenstance, some one in a zillion chance occurrence that would lead to life? And you can study that in a scientific manner by going to our neighboring planet. And that's why there's a Mars Renaissance. That's why there have been so many missions that have gone to Mars in the last 10 years. And the most recent one, and in some regards the most fun, is the Mars 2020 rover. And this rover is kind of like the Curiosity rover. It's about the size of a small vehicle. It has 6 wheels, and it's got an imaging camera, and it has a bunch of instruments at the end of an arm that can, in fact, core and take small cores and put them in little test tubes and seal them and save them for a potential return to Earth. So this mission is the first of what we would call a sample return mission that could come back from Mars and bring samples from Mars, from a known location on Mars with a known stratigraphy and a known setting for study on Earth. And the thing that we're looking for is bugs. We want an ancient habitable environment at about the same time that liquid water was stable here on Earth and life formed. And where's the best place to go? So the place that was selected is called Jezero Crater. It's a large impact crater that's quite old. You can see there's a channel that enters and breaches the wall of the crater here. And there's this feature that I'll call a delta. And to geologists, there aren't that many features that you can look at from space and know exactly how it formed. And a delta is one of them. And it forms only when you have a large river carrying sediment that enters into a standing body of water. And what happens is the water enters from the river, enters, the velocity of the water drops, and the sediment drops out into this lake in a very deterministic way, where you have the coarsest sediment deposited close to where it first enters the water. And as you go further and further out, it becomes finer and finer grained until only you have clays that are deposited that slowly drift down from the water. And on Earth, these are among the most biogenically active locations on our planet. You can think of this river as carrying all these nutrients entering into this stable, quiet habitat of a lake. And we sort the sediments by grain size from near the mouth of the channel to out on the edge. And you can tell by looking at the layers in the delta exactly which environment you have. This particular crater with this delta has clay minerals that were deposited in what we call the bottom set beds, which are just filtering out of the water. And these are the places where on Earth, the clays sequester organics and sort of put them in little tombs that keep them safe from subsequent loss, so that you could go there and find these sediments and find the evidence of life if it existed at that time. So that's why Jezero Crater was selected, and that's why we went to this particular location. It did, in fact, carry a hitchhiker. It was planned. That hitchhiker was the Ingenuity helicopter, and it was put on as a technology demonstration to show that heavier than air flight was in fact possible on Mars. The Mars atmosphere is about 6,000ths the pressure of the Earth's atmosphere, so it's very thin. And it took quite a bit of work looking at analogs and so on, and pumping down vacuum chambers to that pressure to show that we could actually design and build a helicopter that could fly in the thin Martian atmosphere. It was carried by the Perseverance Rover, which looks a lot like the Curiosity rover. There it is sitting on the surface after it was deployed. It is a technology demonstration. It was designed to have 5 flights over 1 month. There were no science requirements. In fact, there was no science team outside of me. I was kind of a scientist that got on, but I wasn't allowed to do any science. That wasn't quite true. I managed to anyway. The nominal flights were just a few minutes. It could fly several hundred meters in range, 5 to 10, maybe could go to 20 meters above the ground. And it carried 2 cameras and nothing else. Well, a few other things, but it had a navigation camera that looked straight down, black and white, and a color camera that looked off to the side. It communicated back to the helicopter. So all communications went from the to the rover to the helicopter, and from the helicopter to the rover to the Earth. So the helicopter always had to stay within, say a half a kilometer or so of the rover for that communication. The idea is to scout for the rover, look at the regional geology, identify the best locations for the rover to look at, and help the rover to traverse. And in order to do that, you need about 10 times better resolution than what we currently get from orbital images of Mars. And these are called the high-rise images, and they're at about 25 or 30 centimeters per pixel. But our experience with rovers driving on the surface is that we want about an order of magnitude better than that. We want about 3 centimeters per pixel to be able to see the rocks and better understand them and do this sort of planning for the rover. So the idea is to have this rover and have it fly around and have the helicopter fly around, help the rover pick the best places to go. This helicopter is a counter-rotating blade design with a small solar panel on top. Inside a warm electronics box is a laser altimeter, an inclinometer, and the various computers that run the sensors, as well as, of course, the little landing legs, 4 landing legs. The whole thing weighs about 1.8 kilogram. Let's see, multiply that a bit to get pounds. But it's not very big, and it goes about 1 meter, so 3 feet from end to end on the carbon fiber blades. It's carried like a pizza in a pizza box on the bottom of the rover. Here it is folded up down here, you can see. And here is a Perseverance Rover in our clean lab at JPL. And there you can see one of the blades. And it's carried inside, this is the pizza box here on the ground. We find a location to deploy it. We drop the pebble shield or pizza box, if you will. We drive away from that, and we find a smooth, flat place in which to deposit the helicopter. The legs fold out, as you saw. So the first one, it rolls down with 2 legs out, the other 2 goes down, and then it falls and drops to the surface. And then the rover, well, we took a picture first, but then it drives away, and we see it from a small distance to make sure that we unlock the blades, and we did an initial spin that you can see on the right. And then the very next thing to do was to try it. Let's see it fly. So here it is, the helicopter or the rover's about 60 meters away. The first flight was up to 5 meters. It held steady, pretty steady, and then it landed back at the exact same place. Again, we had to pick a smooth, flat location for the helicopter to land at, because it's not very big, and obviously you can't land it on a rock. That would be a bad day on Mars. So there's our first. So we were happy campers. Well, and everybody was happy because it's just a totally cool little gizmo. The technology demonstration was 5 flights, and the first 5 included taking off and landing. We had one where we moved a couple of meters. We went one where we went 50 meters out and back. And then we flew 133 meters out and back to find a new place that we could land, because we thought that the orbital images were not high enough resolution to be able to pick a safe landing site for the rover. Sorry, for the helicopter. Here's the flight to the new airfield. Here is where we deployed. Our initial flights were in this areas, which were scouted out by the rover. And we saw a relatively smooth location down here that we thought would be suitable for landing the helicopter, but we didn't know what it looked like in high resolution. So to see it, we flew all the way down there, took some pictures, and flew all the way back. Here is the flight coming back from that epic flight, if you will, 133. It's coming all the way back to the same place we started, and then it is landing. There it goes, landing back down. And we took the images that were collected from the navigation camera, these black and white images, and we looked at them and said, hey, this looks good. There's no rocks there, so we can fly down there, and that would be our new airfield. Well, if you think about this for a little while, this is kind of an inefficient way to get around town, right? Every time you want to go to a new place, you have to go fly there, image it, and then go back, and then fly there again. So each time takes 2 or even 3 flights to get there. And we said, well, that's sort of limiting in how far you can go. And it's limiting in trying to keep up with the rover on its traverse. So the next flight was, in fact, down there, taking those images. We looked at the images. Here's the high-rise images at the base. Here are those navigation camera images overlaid. And you can see, we kind of thought there might be a rock there, and there's a whole bunch of rocks, and it's a ripple as well. And you can see we're resolving rocks at the scale at which we would be concerned for landing the helicopter. So this looked pretty good. And we kept staring at this. We kept saying, well, gee, if we saw a place that didn't have any of these spots, so here's the high rise beneath it, and here is the helicopter image we put on top, and you can see there's just no rocks there whatsoever. So if we look at the images in high rise and we see locations that show not even an inkling of a rock, then it's probably going to be safe. And here's what it looks like from the surface. So, and we've used this technique now for 1, 2, 3, 4, about 10 other flights. We're at flight 19, so 16 more flights. And we've been successful every time. And this is my portion of the job of the helicopter, is to find the next airfield. Okay, so here's the flights to date. The yellow shows the rover as it drove down around the edge of this very rough area with these large ripples and outcrops called CETA. And it drove all the way around it because it was too afraid to go into it. But we, because we can fly, with our helicopter, flew straight across it in an epic flight that was 600 meters long and landed here before the rover ever got here. And then we continued to scout out into these areas where the scientists had an inkling that they might want to go and see, but it wasn't clear that there were traversable paths or that it was safe to do so, to go inside this area called CETA. So here's where we landed, down in this location. So here's the delta. We overshot a bit, landed here, and we drove down and around here. That's shown in this situation here. And what I'll show you is some of the flights here that we did to help out the rover in its path and in its job. So this location is right here. This is an area that in the orbital images, the scientists felt that there would be good samples of rocks to go and investigate, but they couldn't tell from the orbital data whether this was a traversable path. And here are stereo images acquired, color stereo, from the cameras on the helicopter that were taken, and the rover planners that plan out the rover traverses determined that this was smooth and safe enough with small ripples, and they could get to this location without a lot of difficulty. So this was our first example of scouting out a path for the rover before it ever got there. The rover was still weeks away from even arriving in this location, and the helicopter was able to determine that those rocks were there and that there was a traversable path to get to those rocks. So this was a real plus. In addition, right next door, you can see what look like these strata or layers that are next to the edge of CETA. So this is CETA here with those large ripples. Here are these outcrops of lighter tone rocks. And it looks like there's a ridge of rocks here and a ridge of rocks here. And we took a flight here that went out, and we imaged on the way back here a series of stereo images of this region to get a better clue about what's happening. And here are those images, and it looks like there's layered strata. So here's a layer, here's some other layers. It almost looks like there's fine layering in between. There's a layer and there's a layer. And the layers within CETA here are diving down beneath. So these layers are older because they're underneath these newer layers that are up top. So this gave us a terrific view of the edge of CETA and some geologic clues as to how this area formed. And we made it into a stereo digital elevation model. Digital elevation models are what we scientists use to measure thicknesses of layers and sizes of blocks, and it gives you quantitative information for measuring and looking at things, and we've been having great fun looking at those. So here is where the helicopter is right now here. I think since we took this, the rover has traversed back this way. The plan is for the rover to drive back pretty much along the way it came, maybe with a slight detour here, and it would then continue up around CETA because this area is too rough in here to actually drive over. We'd continue around here all the way across to the edge of the delta and image the delta layers here that are so beautifully exposed here, and then scout out here to figure out which way to go up on top of the delta. And we think this is a likely traverse path. So with this in mind, the idea is to get the helicopter there first and to acquire some of these stereo images along the edge of the delta, and in fact image this potential valley where the rover might drive up to the top of the delta, and see if we can get stereo data to determine whether there are traversable paths, and to get some initial data on the edge of the delta that would give the rover a better idea of where to look in more detail from the ground. And to do that, the plan is for the helicopter to hop up and go back pretty much to this region. And we're hoping to do one of two things. One is to follow the rover all the way around like this, but that's going to be a lot of flights. And the other is to fly across CETA, which of course the rover can't do. And this would be awesome areas to take detailed images on the way. Get over here before the rover does and begin to investigate the edge of the delta and help it on its next phase of exploration. So that's the Ingenuity helicopter, designed for 5 flights, and now we're at 19. So it's still going.
Wow.
And we have a new lease on life. We're funded for the rest of this year, as long as the helicopter continues to operate, to try to help the rover in its path and in its job.
Mm-hmm.
That is just fantastic news that we get to continue to see the helicopter in action and get great results out of it as well. And I have a couple of questions to start us off. We've had several in our YouTube chat that we'll get to. I'm curious, do you have any idea how CETA formed? Are those volcanic layers, or were those laid down some in another way? I thought I had heard they were volcanic, but what's the word from you? You're the one exploring it.
That's right. And so the rover has lots of detailed instruments. We have microscopic images. We have chemistry and mineralogy from them. And so far, both CETA and the layers above it are in fact volcanic, or what we would call plutonic rocks, which are volcanic rocks that cool more slowly at a deeper level. So even though we saw those strata at the edge of CETA, those are in fact volcanic layers of one on top of the other. And so we're probably looking at an eroded surface, right, to erode CETA to get down to the material beneath it. That kind of makes sense when you look at all those ripples. That's aeolian activity that's moved material around and put it into specific places. So that isn't at all what we expected, right?
Yeah.
The idea is to go find sedimentary rocks. And we got there, and actually, to be fair, there has been quite a science debate about what the rocks on the floor of Jezero Crater have been. And one of the hypotheses has been that it was in fact volcanic. I'm very skeptical that the delta, where I've told you that we know those are sedimentary rock, that's where we're going to have sedimentary rock. So there's obviously an interesting interplay between, are those the volcanic rocks that preceded the delta, and the delta was deposited on top of them? And those are the kind of things that we'd hope to begin to ferret out as we move around. Yeah.
Well, that's kind of exciting. I mean, you said plutonic rocks from very deep. That's
deep?
an interesting result.
Yeah, that's right. And of course, on Earth, the way we get rocks from deep up to the surface is by tectonics and mountain building and plate tectonics, which has mobile plates on the surface that crunch around into each other and raise up giant mountains. We don't have plate tectonics on Mars. So how do you get exposures of rocks that have been at some depth? Now, these probably weren't that deep. The crystals aren't giant. But they are dominantly what we call olivine. And olivine is the first mineral to solidify out of a mantle melt. And mantle melts that come to the surface quickly are called basalt. That's the most common rock type on Earth. All of the ocean floors are made of basalt, and a big chunk of Mars is made of basalt too.
Yeah. One of our people on YouTube typed in a question, wanted to know a little bit more about the Wright brothers fabric that is included with the helicopter, and whose idea was that, and what you think about that.
Yeah, so we carried a small swatch of the fabric used on the wings from the Wright brothers, and it's to signify this is our first powered flight on another planet, and that's pretty significant. So yeah, we were pretty happy about that.
Yeah, that was a really nice way to honor that initial flight and to commemorate this first flight on Mars.
Yeah.
And another person typed in, wanted to know, how long is it going to take us to get to the Delta? And I'm going to modify the question a little bit. How long will it take the rover? And how long would it take the helicopter if you were just a beeline there?
If we didn't need, so remember, we're kind of tethered by the distance we have to stay to be able to communicate, right? We can't get more than 500 meters to, maybe a kilometer at most from, and we need kind of line of sight too. So we can't have mountains and hills. And we've been doing very careful looks at the topography to make sure that the places that we fly to would have a comm link to the rover when it's there. And that if we were to try this flight across CETA, we probably need to land somewhere in the middle there, and we need to have communications back as well. So it's unclear. I would say it's certainly weeks to maybe a month for the rover to go all the way around. It partially depends upon how much science it does, and if it decides to sample other rocks, that slows you down. The rover, just the last downlink from the rover did the longest drive on the surface of Mars ever. So that was 263 meters using a system called AutoNav, in which the rover takes images from the front and determines if there are obstacles that it needs to go around, and it automatically changes its path to continue going without Earth in the loop, what we call Earth in the loop. And that enabled it to go much further than we could. The last record was 200 and maybe 10 meters by the Opportunity rover in Meridiani Planum, which was extraordinarily smooth and flat, by the way. And Jezero is much more complicated surface-wise. But this, using this technique, the thought is they can do these long drives and make its way all the way around. So, weeks to a month, I would say. We're looking, if we do fly across CETA with the helicopter, we're probably looking at a handful of flights, a few flights, 3, maybe 5, something like that.
Mm-hmm. Okay. Well, fantastic. Now, you mentioned early on in your talk that this is a sample return mission in a way, although at least this is the sample gather mission. We've talked about that with our All-Space audience before. Now, the return mission is going to have to go to the locations that the samples have been stored. Will they be stored in multiple locations on Mars, perhaps? And will they bring another little helicopter to help find them? Or what is the plan?
That's a possibility. Sample return, it turns out to be a very complicated effort. So first of all, what Perseverance Rover will do is it will take dual samples of everything that it decides to collect. And it will take those until it gets to the edge of Jezero Crater, at which point it will lay down one of each of those dual samples in a cache that will be near the mouth of where that channel enters and breaches the wall of the crater. Okay. And that would be roughly the nominal mission for Perseverance. So if something happens after that and it fails or whatever, that cache would be available. If it continues to go as long as a lot of the things that we design and build, which don't have any consumables really on board, that can go years and years. Opportunity lasted 10 years before. So if it keeps going, it will climb out of the crater into the adjacent highlands called Nili Planum, and already identified are a whole wide variety of rocks and materials that are not available inside the crater. It would drive and sample those, including the one of each that it brought from Jezero. And when it gets to the end of its traverse, it would deposit another cache. And then the subsequent mission would land nearby either of those caches, whichever one is decided to be the best, okay, at a location that is smooth and flat enough for the subsequent fetch rover from the second mission to go and collect those samples. So each one is sitting in a little test tube, and they're just sitting on the ground waiting for the next mission to come. So in fact, we're already looking at landing places and cache locations for those samples and for the next mission. So the next mission carries two things, or it's two missions that carry one thing each. One of them carries a fetch rover that is going to land as close to that cache as it can. It will go and get those samples, and it will place them into a round, I'll call it a bowling ball. Okay, but it's hollow inside, and the samples go inside this bowling ball, and the top goes over and seals, and that's the sample canister. And it takes the sample canister and it drives back to where they landed, and it puts it on top of a rocket, and that rocket blasts that sample canister into orbit around Mars. And that canister then orbits in a stable orbit, going around and around and around and around until some future time when the third mission, or fourth, depending upon exactly how you engineer it, comes and finds that bowling ball orbiting around Mars, captures it all robotically, brings it back to Earth, and lands it at the Utah test range. And then you go collect that bowling ball sealed so that no Mars material comes back to Earth except what's inside this sealed bowling ball. And you take it to a yet to be built facility that is safer than the Center Disease Control facilities for the worst diseases we have on Earth. And you put it in there so that no Mars material can get into the Earth's biosphere without first checking it out.
Wow. Well, that sounds like, I don't know. I shouldn't be holding my breath for this to happen.
It's
certainly not.
So right now, the two chunks of the sample return are being planned by both NASA and the European Space Agency. And they're talking about the late in the 2020s for those missions perhaps going. So it may not be that far along, but yeah, I wouldn't hold your breath for those samples coming back.
Yeah,
right away.
I wonder whether we're going to see one of Elon Musk's big rockets land.
There'll be a Starbucks up there.
Yeah, but I mean, that would, in my opinion, that might be the worst thing possible, to have a human go pick it up, because the contamination possibilities, everything else. That's just horrible. And robotically getting it is the way I want to do it, to really get the best out of this science.
That's right. And you won't know if life started on Mars. If you send people there and you haven't answered that question, you won't know, because people are dirty. I mean, we have bugs all over the place. We will certainly contaminate Mars if we send people there. So yeah, the idea is to do this in a super clean manner with robots. Yeah.
You said something that's really remarkable to me, and I've been studying, I thought I'd been studying properly, this mission. Obviously, I knew you folks are going after the Delta and everything down in Jezero. And of course, I do know the gap out onto the west where that goes up into the river valley. Your ambition to get into that river valley and then up and out and on to Nili Planum, that's almost a second mission.
Yeah,
I had no idea.
Yeah, and that hasn't been approved or anything yet. I mean, obviously the rover's got to be, capable of doing it, but we are already looking at traversable paths that will allow us to go up there. The rover has, limits to, if it's on loose soil, it can drive up slopes about 15 degrees. If it's
about how fast can it traverse, and does it have any software to keep it from, say, driving off a ledge you didn't see? Are there protective things built in?
Yeah, that's the auto nav I was talking about, where it actually takes images every wheel rotation or so, and it is stereo images, and it calculates the sizes of obstacles, and if it sees nothing, it will stop too.
Mhm.
But we have high enough resolution from the high rise that I showed you to we're not going to purposely drive it off a cliff. That's not, I mean, that's just not
No.
a good idea.
Yeah, that was one question from the audience, but it certainly is nice to know we have those checks built into the helicopter flying.
And the reason for those checks is that you can't joystick a vehicle that's on Mars. So
Yeah.
the one-way light time between us sending a signal to Mars and the rover getting it on the ground can be 10 to 20 minutes. So think about it, if you were trying to virtual reality this, right? And you had a little joystick. Well, by the time you got the picture of the rover going off the cliff, it already went off 10 minutes ago. It's too late. Right. So that breaks all your operations up into daily, what we call plans for that sol, that day on Mars. Yeah. So the way the ops team works is that you have all these scientists and engineers huddling together, figuring out what to do the next day. At the end of the day, the rover sends back all the telemetry that it collected during that day. You get it, and you work for 10 to 12 hours designing the commands for the next day. By that time, it's morning on Mars. The rover wakes up. You send this command load with all the things it does, and it goes and does them. You can't watch it while it's doing it. It's like sending your kid off to college. You did all the things you could to keep them out of trouble, but then they're on their own, Yeah. You can't help them. They're there on their own. And it does everything that entire day with you don't have a clue. You can't see it. You don't watch it, nothing. And at the end of the day, it sends back everything it did. And so that's what's called Earth in the Loop. And this, in the early part of the mission, we work on what we call Mars time, which is 38 minutes longer than Earth day. So an Mars day is 38 minutes longer than an Earth day. So in 2 weeks, your schedule has moved forward 12 hours. And in 6 weeks, it's rotated around the clock. So think about that. That's worse than jet lag. That's jet lag all the time. It kills you. You die. It's horrible. But you do it in the beginning because that resource is so precious, and you want it to get out and do these great things that you can. But then you get to the point where you're so exhausted. You haven't taken your clothes to the cleaners. You haven't gotten your hair cut. You haven't done anything because you're not awake at the right time of the day to do it, and you're so busy working on this rover that you go to Earth time, and then you become a little bit less efficient because you start losing days that don't line up where there's days.
Yeah, absolutely. Last couple of questions before we move on with the rest of our program. Someone asked about dust building up on the helicopter's solar panel. Do the blades and the motion help keep dust off of that at all? Have you seen, what's our concern?
Interestingly enough, we just had a small dust storm on Mars just a couple of weeks ago. The rover and the helicopter, the rover's not solar powered, but the helicopter is. Helicopter saw a power drop, but unlike surface missions like InSight or the other rovers that have dust that continuously falls out of the atmosphere and degrades the power situation. And in fact, for InSight, which is a lander that doesn't move, it has a seismometer and it's listening for Mars quakes. The dust is built up so much on the panels that the mission's going to come to an end because of that dust buildup, and it hasn't been cleaned like they were for Spirit and Opportunity, where we had these vortices or dust devils that managed to clean off the panels. Unlike all of those, we're guessing that because of the motion of the helicopter, that we've had no dust buildup on the panels whatsoever. And it's not just because of the rotors. They're actually below the solar panel, which is above them. So, but just the action of flying and moving around appears to be enough that there's been no degradation of power for the helicopter. So that's a plus.
Yes.
Yeah, that's a big plus. Well, I thank you so much for joining us tonight. I think we might have lost your video, but we've had your audio at the very end here. Maybe it's due to Mars time. I'm not really sure. But anyway,
it's all lagged.
Yeah, thank you so much for joining us. It's just fascinating to hear all these details about this wonderful mission to Mars.
Here.
And we'd love to have you back again next rotation. You know, when you've got another chance again and you've got more information to tell us. Maybe when we make it up onto the Delta, I don't know. But this is just, I love this mission. I love that the helicopter is doing even more than we thought it could. Ingenuity is just, it's really been a fascinating addition to our capabilities on another planet. The fact we're flying through the Martian air as thin as it is just incredible. So thank you for your part, and really exciting times for us and our audience. And thank you again for joining us.
My pleasure, and I look forward to our next time.